Students, last time we have seen Hale's law and complexity of molecule and deviation of distribution law. Today let us see molecular complexity and deviation of distribution law. Last time we have seen how solute undergo association in one of the solvent, and in that case we have seen how Moore's distribution law deviates from normal distribution law, and we have seen the modified distribution law, or rather the mathematical expression of modified distribution law in that case. Let us see today how solute dissociate in one of the solvent during distribution, and when it dissociate in either the solvent, how Moore's distribution law is modified. Let us take an example of distribution of a solute like acetic acid between ether and water. We know acetic acid when it goes in water like polar solvent, it dissociates into its constituent ions. So what happens in this case? When we take acetic acid, aqueous solution of acetic acid, and mix it with ether and take a mixture of these two in a separating funnel and shake it well, we find that acetic acid distribute between ether and water, and the distribution of acetic acid between these two immiscible solvents we can show with the help of one simple experiment with which you can understand how a solute in general distribute between a pair of immiscible solvents. So let us perform one simple experiment with which we can understand the distribution of a solute in between a pair of immiscible solvents. So let us take one separating funnel, and in that separating funnel, let us take water, 100 ml distilled water in it. Now let us take 100 ml ether in the same separating funnel. Once we take both these solvents, water and ether, in a separating funnel, let us add acetic acid in it. When we add acetic acid, a solute in this case in liquid state, it distributes between two immiscible solvents on shaking. Look at this, we find that water, there are two layers. Lower layer is aqueous layer and upper layer is organic layer, in this case ether layer. So when we shake vigorously, we will find that acetic acid distribute two immiscible solvents. Here we cannot see the color because all these solvents, both these solvents are colorless. Acetic acid is colorless, but we can see very easily there are two layers. One is aqueous layer, the lower layer is aqueous layer, the upper layer is organic layer or ether layer. In this way, we have seen in general how a solute like acetic acid distribute between a pair of immiscible solvents, in this case water and ether. Now, here, as per the molecular state of the solute is concerned, we will find that acetic acid, when it goes in water, it dissociates into its constituent ions. On the contrary, in ether, acetic acid remains in normal state, and the equilibriums in this particular case existing. We can show the equilibriums existing in this case with the help of these two equations. The first equation, CH3COH H2O in H2O is in equilibrium with CH3COOH in ether. Let us suppose this is phase 1. Let us call this is phase 1, this is phase 2. Or rather, this is phase 1 and this is phase 2, or solvent 2, and here it is solvent 1. We will see that in solvent 1, acetic acid initially, acetic acid distribute between two immiscible solvents, water and ether. This one, the first equilibrium, whatever acetic acid which goes in water, it further dissociates into its constituent ions, and the equilibrium in that particular case is CH3COOH in H2O. It dissociates, or rather, let's write it here, aqueous aqueous plus CH3COO minus aqueous. Equation number 2. Here we will find that this expression, the second expression, clearly shows that acetic acid, it dissociates into its constituent ions H plus and CH3CO minus in water. On the contrary, it remains as it is in ether. It do not undergo any change as per the molecular state of the acetic acid is concerned. So, in short, we can say that in this particular case, acetic acid remains in normal state in ether. On the contrary, acetic acid in aqueous layer undergo change, and the change in this particular case is dissociation of acetic acid into its constituent ions. In other words, the molecular state of the solute acetic acid in this case alters in water. So let us apply distribution law to the equilibriums, these two equilibriums. Before that, let us suppose the concentration of acetic acid In normal state, let concentration of acetic acid in water in ether is C1, and below in ether acetic acid remains in normal state. Let concentration of acetic acid, rather the concentration of total acetic acid CH3COOH in water is C. Let us suppose the degree of dissociation of acetic acid in water is alpha. So we can very easily go the concentration of acetic acid at equilibrium in this particular case. At equilibrium, the concentration of acetic acid will be equal to 1 minus alpha, and the concentration of H plus is alpha, and the concentration of CH3COOH is also alpha. Okay. So here, once we know this, the concentration of what acetic acid is 1 minus alpha into C2. Substituting for the value of the concentration of acetic acid in normal state in aqueous layer and in ether layer in the mathematical expression of distribution law, that is Kd is equal to C1 upon C2. We get Kd is equal to C1 upon C2. Here C1 is equal to C2, no doubt, but as far as C2 is concerned, the concentration of undissociated acetic acid molecules in aqueous layer is 1 minus alpha into C2. So here we find that the expression, whatever expression which we have seen, C1 upon C2, for what the normal Gauss distribution law is modified or is to be modified in this particular case, and the modified expression is Kd is equal to C1 upon 1 minus alpha into C2. In this way, we have seen how Gauss distribution law modifies when solute like acetic acid dissociate in one of the solvent, in this particular case, water. So, in this way, we have seen how Gauss distribution law modifies when solute undergo dissociation in one of the solvent. Now, let us suppose instead of solvent to some another solute, hypothetical solute X, it dissociates into its constituent ions in solvent 1. So in that case, obviously, if degree of dissociation is alpha, in that case, the concentration of undissociated X molecules will be equal to 1 minus alpha into C1, and as the solute X do not undergo any change in solvent 2. In solvent 2, the concentration of solute X will be or is C2, and the concentration of solute X in solvent 1 is 1 minus alpha into C1, and obviously the distribution coefficient KD in this case is 1 minus alpha into C1 upon C2. I hope you have understood how Gauss distribution law modifies when solute undergoes dissociation in one of the solvent. Sometimes the solute may dissociate to some extent in both the solvents, solvent 1 and solvent 2. In that case, the Gauss distribution law or the modified Gauss distribution law is like this: 1 minus alpha dash into C1 upon 1 minus alpha into C2 is equal to KD, where alpha dash shows degree of dissociation of solute in solvent 1 and alpha shows the degree of dissociation of solute in solvent 2. So in this way we have seen how Gauss distribution law modifies when solute undergoes dissociation in either one of the solvent or both the solvents. Let me conclude with this. As per molecular complexity is concerned, when solute undergoes dissociation, in this case, we have seen with the help of dissociation of acetic acid in aqueous layer, the partition coefficient in this case KD is equal to C1 upon 1 minus alpha into C2, where C1 represents the concentration of undissociated molecules in solvent 1, or rather in this particular case ether, and C2 the concentration of undissociated molecules, or rather the total concentration of acetic acid in aqueous layer, that is water, and alpha is degree of dissociation of acetic acid in water. So with this, I hope you understood how Gauss distribution law modifies when solute undergoes dissociation in either of the solvent or in both the solvents. With this, I will stop here. Next time, we will see the numerical problems based on Gauss distribution law and the modified Gauss distribution law. Thank you very much.